study guides. We'll start talking about these. I think we're on right now. Let me check the volume. Chat. Chat. Volume check. Okay. So this is part 2, which is really part 1. Yeah. All right, so here we go. Question 1. It's been estimated that around 30% of frozen chicken contain enough salmonella bacteria to cause illness if improperly cooked. A consumer will purchase 12 frozen chickens. What's the probability that the consumer will have more than 6 contaminated chickens? So first thing we need to do is recognize the fact that we have some kind of a binomial distribution. Okay. So if we say X is equal to the number of contaminated chickens, then X is binomial. We are picking 12 frozen chickens, and the probability of success here is 0.3. And we're saying success is equal to a contaminated chicken. Every time I do this, I want to put quotes around success because it's not really success if you have a contaminated chicken. Unless you're trying to poison someone. Yeah.
Do you have to define success?
No, you don't have to, but it's a good idea to get in the practice of really thinking about what success means. Okay, so then this is pretty straightforward. Then we want to know the probability that the consumer will have more than 6 contaminated chickens. So the probability that the number of contaminated chickens is more than 6. Okay. So let's quantify. Let's think about which quantities of contaminated chicken. Greater than 6 means 7, 8, 9, 10, 11, 12. So what we are looking for then is the complement of that set, 7, 8, 9, 10, 11, 12. And that complement is less than or equal to 6.
Where's our pizza?
Huh?
Were you able to print it?
No, I didn't get it.
Hey. What? Hey. Hi.
Okay, let's do this in the calculator. So 1 minus the probability. Let's see, that's a binomial distribution. 12 trials, 0.3, and 6. So we're getting 386. Pretty small chance. It's about a 4% chance. Questions? No? Remember that you have to use a less than because that's the only thing your calculator can take, less than. Unless, of course, at the 89 you don't have to. And the Nspire you don't have to.
Oh, okay.
But I think.
No.
No?
It's like, I think
Low and
you
high?
Can see, yeah, there's a low. You can adjust it.
Question 2. The probability that a certain machine will produce a defective item is 0.2. And we have a random sample of 6 taken out of this machine. So X would then be the number of defective items. And then again, success is a defective item. Okay. So then X is a binomial situation. We have taking 6 items, and the probability of that item being defective is 20%. That's a really bad machine. 1 out of every 5 things are going to be defective on average. It's a bad machine. So we want to know the probability that X is greater than 5 or more. 5 or more. So greater than equal to 5. So there's actually a couple ways that we could define this. One way to define this is, well, let's just think about which of our outcomes are greater than equal to 5. Just 5 and 6, right? So we could say the probability that X equals 5 plus the probability that X equals 6. That's totally valid. And it's actually going to be kind of easy to do. Or we could do the complementary again. 1 minus the probability that X is less than equal to, in this case, is going to be 4. One of these 2 ways would be fine. Let's do that way later. Let's do this one right now. Back to the calculator. We're going to do binomial PDF. Binomial PDF is A. That didn't work.
Why is it a PDF, not PDF?
We're doing probability that X equals 5 plus the probability that X equals 6 right now. Yeah, so we're doing 6.25 plus 6.26. So if we add these 2 binomial PDFs together, that's the probability that X equals 5 plus the probability that X equals 6. 0.0016. And then we'll do the OR. Or we could do it this way. Nothing wrong with this. And that's 1 minus, now the binomial CDF, six point 2 and 4, right? Same thing, 0.0016. So it's really the same. Okay. I don't know which one of these 2 calculations you're going to want to do. Both are perfectly fine. Okay. Question? 3? Survey asks a random sample of 1,500 adults in Ohio if they support an increase in sales tax from 5% to 6%. Okay. Tell you blatantly right now that 5% and 6% is only there to throw you off. Okay. With additional revenue going to education. Let X denote the number in the sample that say they will support the increase. Okay. So we don't really have to write that down. And then we know that 40% of all adults in Ohio support this increase. Okay, so we have a binomial situation. We're looking at 1,500 people, and the probability that they're going to support this is 0.4. So X is number of people who support, is it an increase? Increase. Okay. So X is a binomial situation. 1,500 people, 0.4. And now we want to know the probability that X is more than 650. So X is greater than 650. Okay. So in this case, you're kind of forced. You don't really want to list all the possibilities between 650 and 1,500. So you kind of have to know what this is. So the complement of this set then, would the complement include 650 or not include 650? I think it would include 650. 650 is not included here, so it must be in the complement. And then straight to the calculator again. So 1 minus the binomial CDF $1,500. That's not 1,500. Probability of success is 0.4, and we want to know, yeah, 650, less than or equal to 650. Zero zero 40. Zero zero 40. Which is less than 0.1, yeah. Okay. Any questions on that? Incidentally, since the sample size is so large, it would be okay to use a normal distribution here, or normal approximation. Should be fine. We're not going to do it. Okay, so question 4. I think I've told many people that this is kind of a part of a multiple choice question where the answer choices were removed. So I think my strategy right now is going to be just to kind of show you what range P has to be within. So we know the sample size is 100. We know the sample size is 100. And if we're going to use a normal approximation, we know that NP has to be greater than or equal to 10. Which means that 100P has to be greater than or equal to 10. Which means that P has to be greater than or equal to 0.1. So this has to be true. But that's not the only thing that has to be true. NQ also must be greater than 10. NQ should be greater than or equal to 10. Which is kind of like saying that N times 1 minus P is greater than or equal to 10. And if you solve that, you get that P needs to be less than or equal to 0.9. In summary, you need to say that P should be between 0.1 and 0.9. So search the answer choices for a P that fits the above description. It just so happened that P equals 1/9. The only one of those that fits between 0.1 and 0.9. That make sense? NP has to be greater than 10, and also NQ has to be greater than or equal to 10. Okay. Let's look at 5. A dealer of cards at the Sands Casino in Las Vegas. Is the Sands Casino even still there? Yeah? I don't think so. Selects 40 cards from a standard deck of 52. Let Y be the number of red cards selected. What would describe this setting? Is it binomial? Well, I think the first thing we need to say is it's not binomial. Okay. The probability of success, which in this case means pulling a red card, changes after every draw, because the cards are not being replaced. Since P changes for every card, this is not binomial. So let's see. A, binomial distribution. B, binomial distributions. C, binomial distribution. D, normal distribution. None of those really work, right? Let's see. Let's look at these again. Let's read these in more detail. Y is a normal distribution with n equals 40 and probability of success is 0.5. That's wrong. Okay, we know it's not a binomial distribution. B, binomial is a binomial distribution with n equals 40 and success provided that the deck is shuffled well. Even if the deck is shuffled well, those probabilities are going to change. So that doesn't really do anything. C, this is a binomial distribution, 40 and 0.5, provided that after selecting a card, it is replaced in the deck and then the deck is shuffled well again before the next card is selected. Okay, and that would take care of this, right? We said that the probability, we said here that the problem was the cards are not being replaced. So if we fix that issue, then we should get a binomial distribution. Okay, so C addresses the issue of replacement. So this is the correct answer. Okay. Six. In a certain large population, 40% of the households have an average income of over $70,000. A simple random sample is taken of 4 of these households. That's a very small sample size. Let X be the number of households in the sample with an annual income over $70,000. X is a number of households. And assume that the binomial assumptions are reasonable. Okay, so we can say X is binomial. How many are we drawing? Just 4. What's the probability of success? 0.4. Here, success means that the household's annual income is over 70,000. I think that's generous, 40%. Which is kind of sad. But this isn't economics, this is statistics. Okay, so what are we trying to do? What's the mean of x? Mu is NP, which is 1.6. Maybe I should write that out. 4 times 0.4, which is 1.6. I would be very uncomfortable calling this a binomial setting, personally. I'd be very careful about that. 7. Oh, again, notice that number 70,000 is another false or unnecessary information. Okay, 7. The probability that a 3-year-old battery works is 0.8. A cassette recorder requires 4 working batteries to operate. The state of the batteries can be regarded as independent, and 4 3-year-old batteries are selected for a cassette recorder. What's the probability that the cassette recorder works? So X is equal to the number of working batteries, right? So that means X is a binomial distribution. Since we have the independence, the probabilities do not change. We have a set number of trials, and we have either success or failure with a probability of 0.8. We want to know what's the probability that the cassette recorder will work. So basically, we're saying that the probability that X is equal to 4, meaning all 4 batteries work. Okay, so this is 4, choose 4. Times probability of success is 0.8 to the 4th power times probability of failure, 0.2 to the 0th power. Okay. And then you write that down, you ignore it, you go to your calculator, and you do a binomial PDF, thank you. 4 trials, probability of success is 0.8. We want to know all 4 work. Yeah, that's 4096. It's about a 41% probability that this cassette recorder will work. Question 8. The Ocho. 2% of circuit boards manufactured in the company are defective. Circuit boards are selected randomly. What's the probability that the number of circuit boards inspected before a defective circuit board is found is greater than 10? Wow, that's a lot of... The probability that the number of circuit boards inspected before a defective board is found is greater than 10. Wow. Yeah, what does that say? Okay, so we're saying X is equal to, this sounds geometric, right? We don't have a set number. So we're saying X is the number of trials before a defective board is found. And we want to know what's the probability that that is greater than 10. that it takes more than 10 trials to find a defective circuit board. Okay. This is equal to 9 circuit boards that work. It's a probability that a circuit board works. That it works? 98%, right? And that's going to be 9 of them times just that one circuit board that fails. So it's work, 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 fail.
Isn't it after 10 though?
Oh, after 10. Oh, I totally have this backwards, don't I? This is the wrong one.
No.
So in other
No, it was
words,
just the 10.
yeah, the first circuit board has, that means we have to have 10 circuit boards that fail, right?
No, that
That work. Sorry.
you had it right. You
10
said
circuit boards that fail. That work. Wow. We have 10 circuit boards that work. After that, it doesn't matter. We're guaranteed that the first circuit board that works is going to be after that 10th trial. So this is 10 working circuit boards. What's the probability of that? That's 0.98 to the 10th power. 8171. 8171. Okay. Okay, so from the free response questions, do you want to do the first set or the second set? Second set?
The third.
Okay, so, yo, this is the overweight one. Be careful what you say. There are,
Some people.
okay, so we're saying a survey conducted by the Harris Polling Organization discovers that 63% of Americans are overweight. Suppose that a number of randomly selected Americans are weighed. Or I don't know what that has to do with anything, but 30 students at a particular adult Sunday school, oh, it has to be adult, are questioned about their weight. Assuming this is a good cross-section of America, show that the conditions for a binomial distribution are met. Well, what are the conditions for a binomial distribution?
2 outcomes.
2 outcomes. Good. Do we have 2 outcomes? We do. What are the 2 outcomes?
So overweight and not.
You're either fat
Overweight
or not.
or not overweight. Condition 2. Independence. Are we assuming that, just because one person's overweight will not affect the next person, right? Okay.
We
So,
just assume that because it says good cross section of America.
yeah. Good point. Independence.
We just say it says so. It's kind of
Yeah, it's kind of implied here.
implied in response.
Implied with good cross-section. Okay. 3. What's the third for this? Set number of trials. How many trials are we doing?
30.
Okay, so we're doing 30 trials. And lastly? Equal amount of probability of success. Yeah, remains 0.63. So yeah, this looks like a pretty good binomial distribution. Okay? So if x is equal to the number of overweight people. Then X is a binomial distribution with 30 people in it and 63% chance of success.
So really they failed, like.
Failed, but you don't have to put these next two lines, but they're kind of there just for, clarifying what we are doing. So let's look at, no, that's not number 10. This was number 14 and 15, right? 14 and 15. What does 15 say?
Find a power that 18 or more of the 30 students in a particular adults in high school class are overweight.
18 or more means that X is greater than or equal to?
18.
Greater than or equal to 18. Great. And I don't think this is too many for us to list out. We'll just think about which outcomes are in this set. Is 18, 19, 20, all the way to 30, right?
Yeah.
So the complement of that set would be everything that is not 18, 19, 20, which is
17.
0 through 17. So 1 minus the probability that X less than or equal to 17, which is just calculator work now.
You never have to explain what we're doing on the calculator, right?
No. You do not have to explain what you're doing on the calculator. 30 trials, probability of success was 0.63 and 17, right? And we wanted to do 1 minus this. One minus that binomial CDF. So 70, 55. $16. How many Americans would you expect to know?
Yeah.
Yeah? No, sure, the normal approximation can be used for n equals 30. Okay, so we need to show that NP is greater than or equal to 10. Which means 30 times 0.63. Yeah, that's greater than or equal to 10. What about NQ? That's 30 times 0.37. Yep, that's greater than 10. Since both inequalities are true, we can use a normal approximation. Okay. 17. How many Americans would you expect to weigh before you encounter the first overweight individual? Okay. So this is, we're looking for the first instance of success, right? Yeah.
For 16, when it says use the normal approximation to estimate the answer.
I forgot to do that. Thank you for reminding me. We're looking for the first overweight individual, which changes this into a geometric setting. We'll finish 16 and when I don't want to jump back to it. First individual, so we're looking for the mean. The mean is 1 over p, which is 1 divided by 0.63. Okay. On average, we would need to contact approximately 1.6 individuals before we contacted an overweight individual.
Is that because 0.6 of an overweight person would be the size of a non-overweight?
No. This is an average.
Okay.
Yeah. Okay, we forgot to finish 16. So there are two things that we could do. The first way is just what is the probability? Well, we need a z-score, right? So the z-score is going to be equal to 18 minus the mean, 18.9. Yeah.
Can I go to the bathroom?
Divided by the standard deviation. And I don't have that standard deviation. You know, we should actually just write these down. Mu equals 30 times 0.63. And sigma is equal to the square root of 30 times 0.63 times 0.37. Did I get that right?
Yeah.
Okay. 2.644. So that's that first z-score. So if you want to know the probability that x is greater than 18, that would be the same thing as the probability that z is greater than negative 0.34. 2 decimals only. And then now that's norm CDF. No. Norm CDF negative 0.34 to 1E99. 0 and 1. So that's 6331.
Really close.
Pretty close. Not really close, but pretty close. Okay, the other thing that sometimes people do is to actually not just get the first z-score, but also get the z-score for 30. Because if you think about it, we can't have, if we're going to figure out greater than 18, it also has to be less than 30, right? So we should get the z-score for 30. So 30 minus 18.9 divided by 2.644. And that's that second z-score. And so the probability that x is between 18 and 30, that would be the same thing as a probability that a z is between negative 0.34 and that 4.2? 4.20. Let's just do that. So negative 0.34 and 4.20. And whoa, you get the same number. 0.6331. Okay. So either way, it's about a 63% chance.
How come for number 17 we don't just say 2 people? Because we can't really have 1.6 people.
Because it's an average, and averages you don't really round them.
Even if it's like required, we can have it.
Because it's an average, we know that it's going to be a. It doesn't necessarily have to be an outcome.
Okay.
Okay, so we took care of 18. No, we're on 18. 18. What's the probability that it takes 5 or more attempts before the first overweight person is found? So we want to know that the x, we've got to redefine x now. X is equal to the number of people, no, is the trial number of the first overweight person. So we want to know what's the probability that it'll take more than 5 attempts. So that's greater than 5. And that means that we have the first 5 people that we contact have to be not overweight. After that, it doesn't matter. So the probability of not overweight is 0.37 to the 5th power. 0.37 to the 5th power. 0069. The cumulative distribution table, do you want to do that one? Yeah. Yeah. 19. So in order to do the cumulative distribution table, we actually need to do the regular distribution table first. So we have to do the regular distribution table. So x 1, 2, 2, 3, 4, 5, and 6. And then the probability that x is equal to x. Okay, so that means success happens on the first trial. So that probability is 6.3. This says that probability happens in the second trial. This is 0.37, 1 failure followed by 1 success. 0.2331. And then this is going to be 2 failures followed by 1 success. So 0.37 squared times 0.63. That's wrong. And then I'm just going to go with what you have. No, I can't. 0.37 squared times 0.36. 0.37 squared times 0.63, right?
Yeah, that's right.
862.
And 0.
And then this one is 0.37 to the 3rd power times 0.63. So we're just going to take that answer and multiply by 0.37 again. 0319. And then multiply again. 0118. And then multiply one last time. 0044. Okay. So that's the regular distribution table. That's not a cumulative distribution table. To get the cumulative distribution table, you need to add everything together. Now the probability that x is less than or equal to x. So So the probability that x is less than or equal to 0.6, less than or equal to 1 is just 0.63. Here you would have to add 0.63 times 0.2331, that's 0.8631. And then we have to add this plus this plus this, 0.95. And then keep on adding down 0.98, 0.99, 0.997. So basically you keep on adding all the way to the left. Does everyone understand? To get 6, you would add all of these together. To get 5, you would add all of these together. 4, add all of these together. Okay. Okay, I'm gonna stop.